Good afternoon, everyone. Today we're going to continue our discussion on multiple linear regression. Last time we defined what multiple linear regression is. We said that the main objective is to find an association, a mathematical function that relates the variable of interest, your dependent variable, with your independent variables. In this class, we're going to learn this in the context of financial data. So we'll look at this as an applied CAPM, okay, capital asset pricing model. Those of you who are my students in FinArts, we learned the nitty-gritty details of the linear regression model, okay, using data that were varied, economics, etc. But this time, we're just going to make use of this in finance. Okay, this is more of a springboard to machine learning in the next few weeks. Okay, so this is what we discussed last time. We have your dependent variable, independent variable, and then a simple linear regression, okay, as shown here in this equation, is just the relationship between your dependent variable and your loan. Only one independent variable. Okay, so this is simple linear regression. If this was multiple linear regression, then you would have several parameters, beta 1, beta 2, beta 3, as slopes for the different independent variables. Your error is your residual, your error term. Okay, this simply means that this is the difference between your actual value, y sub I, minus your predicted value, or your y hat. There are certain assumptions in classical linear regression model. Again, class, I will not discuss this anymore. Please watch the videos, class, so that we're able to save time and we're able to discuss the other important things. Okay. So linearity, which tells us that y and x should be linear. It doesn't make sense if your y and your x are related quadratically. Okay, so suppose if you plot your x and y, if it looks like this is your y, this is your x. If you plot them, it looks like this, or it looks like, say, maybe a polynomial. Okay, it doesn't make sense for you to use a linear regression model for this. Okay, the relationship between your x and your y should be linear. Okay, also, one other very important thing is that your residuals class, your error terms. When you're assessing your model, many of the tests there, many of the assessments are about residuals, aka errors. So number one is your error term should not be correlated. So I don't think that I discussed this last time, so let me discuss this now. Generally, there are three types of data that we're going to be exposed to. Number one is cross-sectional data. Cross-sectional. Then you have your time series data. Time series, sorry for not having to type the whole word. Time series, and then your panel data. Panel data. Okay. Now we can look at the differences of these three types of data in terms of the number of units and the number of periods, time periods. Sorry for the writing class, it's terrible because I'm using my mouse. My digital pen does not seem to be working. Okay, so cross-sectional data class, when with reference to the units, you have many, and with reference to your time frame, time period, you have one. Okay, let's explore data. Let's suppose you were you were studying the return on assets or net interest margin of banks. Okay. So a cross-sectional data would be you have many banks. Okay, let's say you have a total of 50 banks. Some are universal banks, some are commercial banks, some are rural banks, etc. But you have many. And you're looking at net interest margin. Net interest margin. But it's the net interest margin for just 2024. So 2024. Okay, so what are the units? Units are terrible writing, sorry, class. Bank number 1, bank number 2, bank number 3, etc., up to bank number 50. So this is bank 50. Okay, and then your net interest margin for bank 1, bank 2, etc., up to bank 50. Okay, what type of data is this? This is what we call a cross-sectional data because you have many units. In this case, our units are banks. Okay, and what are your time periods? How many do we have? We have one. Okay, 2024. We're looking at the net interest margin of all your banks in 2024. Okay, so that's a cross-sectional data. Now for a cross-sectional data, this requirement, independence of errors, are irrelevant. Okay, they're irrelevant. Okay, so for example, you have this actual value of your net interest margin. Let's suppose you're predicting this, and you have your, let's say, several predictors, x1, x2, x3, x4, let's say, and then you're able to come up with your predicted value, y hat. Okay, and you can compute now for your residuals. How do you compute for your residuals? You get the difference between your actual value. So this is your predicted NIM. This is your actual NIM. Let's suppose this is, for purpose of example, this is, let's say 0.5. The NIM for bank 1 is 0.5. Now the predicted value is 0.48. Okay, so they're not the same. Okay, so you have a residual here of 0.02. The difference between your actual and your predicted value. Now, how do we relate that now to the independence of the errors? Now, each of the banks here will have their residuals, right? Some will be negative, where your predicted will be more than your actual value. Some will be positive. Now, so you have here the order of your residuals. Now, the question is, how were the units arranged? So possibly the units were arranged, let's say, alphabetically. Okay. So because of this alphabetical arrangement, you have this arrangement of your residuals. But will it matter if you change the order of your units? No. No, you can randomly arrange this, or you can arrange this according to age. Those banks that were established first will come first. So when you do that, when you change the arrangement of your units, your residuals also, of course, will change. And now your epsilon 1 and epsilon 2 will now be different. So what will happen now to your errors that are consecutive? It will change, class. It will change. So it doesn't make sense to look at the independence of errors when you're dealing with cross-sectional data. Okay, I hope you got that, because if you change the order of the units, then necessarily you'll change the order of your residuals. But things are different if you have time series data. Okay, so for time series data, let's suppose you have For time series data, you have only one unit, and then periods will be many. So that's a difference. It's interchanged. For cross-sectional data, many units, one period. For time series, one unit, many periods. So back to this example, banks. For time series, you're only looking at bank number one. And then the net interest margin, you're looking at it, let's say from 1970 up to 2024, and only one bank. Bank one, you gathered all the net interest margin from 1970 to 2024. So that's your time series data, as distinguished from cross-sectional data. So what happens now? You now have a logical order. Your logical order is by time, 1970, 1971, 1972. Okay, and once again, you have your actual NIM, and then you compute for your model NIM, your predicted NIM. And then you have your difference, residual. Actual NIM sub T minus your predicted NIM sub T is equal to your residual. Now, in this case, your data is arranged logically by year, 1970, 71, 72, 73, so that your residuals will also be arranged logically. Is it possible to rearrange this randomly? No, because you have to maintain the logical structure of your data. Okay, there's a reason why you just can't put 1980 first, and then 1975, and then 2020. Can't do that. So in that case, there's a logical arrangement of your residuals. So for that case, you can really take a look at the independence of your errors. Is the error of 1970 related to 71 or 72 or 73, etc.? Is the error of 1975 related to 1976? So there you can get the relationship between them. And we're saying here that the errors should not be dependent. They should not be related. If your errors are related, then you have a problem. That means your model was not able to capture that that phenomena of your errors being correlated. Okay, so independence of error terms is true for time series and for panel data, but not for cross-sectional data. For panel data, it's many units and many periods. So for example, our bank, we have 50 banks. Okay, so many units, 50 banks, and then many periods. Let's say we were looking at the same thing, net interest margin, say from 2010 until 2024. So for 2010, we have the 50 banks here. Okay, and then for 2011, you have 50 banks. Until 2024, 50 banks. So, and all these banks are the same. Okay, so each year you have 50 observations of NIM, 2010, 2011, until 2014. So that's 15 years times 50. Okay, so that means that you have 750 observations. Okay, so panel data actually is the most robust of all of this. If you're going to do regression, panel data is the best. Okay, because you'll be able to get insights from both the unit. Okay, you can see if there's a difference between each of the units. Is bank one different from bank two different from bank three? Or you can also take a look at the difference between years. And that's not possible in time series nor cross-sectional data. Okay? All right. So homoscedasticity class just tells us that the residual should be constant. I discussed that in the other video, normality also, and also multicollinearity. So I'll not discuss that here. please refer to that to that video so that we save on time. All right. So I discussed also last time that the regression is all about minimizing your residual squared. Okay, so the line of best fit, the regression line, is the line that minimizes the residual squared. Notice it's not minimizing the residuals, because if you sum the residuals, it will amount to 0. That's why we don't add up the residuals. Rather, what we add up is the square of the residuals. That's why I said in the previous meeting that the method is called ordinary least squares. The process of determining your regression line is called ordinary least squares. Least here means L-E-A-S-T, the minimum. Squares here is the square of your residuals. Okay? Squared residuals there. That's why it's called ordinary least squares. So just quickly, you're taking a look at the actual value of y minus the predicted. Remember, the definition of the residuals is the difference between your actual value and your predicted value. So you get their difference and then sum it. Okay? Or it can be written as your actual value minus this one class. Your predicted value is this one. Beta null plus beta 1 times x sub I. And then you perform this, you can use calculus in order to determine your beta null and your beta 1. Okay, modeling your OLS means identifying your parameters, beta null and beta 1. Okay, so so this one class I discussed. Okay, now for those of you who are doing this for the first time, please load. You have already quant mode performance analytics ggplot to make sure they're loaded. Okay, or just run this library, or just I don't think I gave this to you, so just go to your packages and then just look for quant mode performance analytics and then just click them. All right, then this one class, we know this coming from quant mode. This is get symbols. And then here we're downloading two assets, SPY and Apple. Source is equal to, same from Yahoo. Beginning date and end date. And then, of course, auto.assign is equal to true because we're not giving it a name ourselves. If you run this class, this will generate SPY and Apple. SPY class is it's an ETF, exchange traded fund, okay, mimicking the movement of Standard and Poor's 500. Okay, so this will be our market. Okay, all right. As I said a while ago, the objective here is for us to be able to use CAPM. Who recalls, class, what's the formula for CAPM? Anyone, please? What is the formula for capital asset pricing model? We will apply regression on CAPM. Anyone, please? Formula for CAPM? Can you chat, please? CAPM, please. I'm sure you have discussed this in several projects, even dating back as far as FMD FINA. Anyone, please? Okay, thank you. See, I have an answer here. Thank you. Thank you, Moises. Thank you, Jello. Jello hindi na kompleto, pero okay lang. So take a look at the yung class, pakitingnan niyo yung ano, no, yung sinulat ni ano, what Moises shared in the chat box. I'll just copy it here. Okay, nakaano pala ako. There, class. That's your CAPM. The excess returns of an asset is equal to the risk-free rate, the returns of a risk-free rate plus a certain slope times the excess returns of the market. Now, this one, class, take a look at this. It follows the structure of a what? Y sub I is equal to beta null plus beta 1 times x1. Okay, and then you have your epsilon here. So the CAPM is actually a regression model, class, where our Y sub I is the returns of the asset, excess returns of the asset. The risk-free rate is your slope. The excess returns of the market is your dependent variable. And your beta, this one, beta A, that's the slope. So exactly, class, CAPM, okay, is a simple linear regression. And then we'll extend it further later on, multi-factor. So you'll have now several predictors, not only the excess returns of the market. Okay, and we're going to do that now. I don't know if we can reach that part, no? But SPY class, SPY returns will be your RM class here, because this mimics the market class. This stands for, this is the GSPC class, Standard and Poor's 500. And your Apple is the asset that we're looking into. Okay, and how do you find risk-free rate? We will look at that next meeting, because we're going to use Fred to get the, let's use a 3-month treasury bills, US, because these are US stocks. Unfortunately, we can't directly download asset prices in the Philippines. Would have been good, no? So Philippine data. But the problem is we haven't reached that far where we can access using our Philippine data. But I think I'm going to set that as an assignment for you to use Bloomberg or Refinitiv to get Philippine assets, and then what could be construed as the risk-free rate, Philippine risk-free rate, and then you create a regression out of that. Load it into get the data first from outside, whether Refinitiv or Bloomberg, and then load it into R, and then create the CAPM model here in R. All right, I hope you have already downloaded the data, okay, as I was talking. Okay, and then here, class, take a look at this. Okay, for those of you who don't have this yet, I'm going to give you a few seconds. Let me just explain here what's happening. If you recall, this is from performance analytics. Okay. Another function from performance analytics is calculate returns. That's the same thing, class, same thing. I just introduced this so that you know that it's not only return that calculate, it's calculate that returns. So what returns are we getting? SPY adjusted. So you know that we can get that from SPY. And type is used in quant mode. In performance analytics, you use method. Method is equal to log. And then we create this object, SPY returns, and you do the same for Apple returns. Okay. Now we know that when we use return that calculate, it will generate an NA in the first row. So we just included here NA.omit so that it will be deleted already. Okay, I'll give you a few seconds. Please run this. And when you're done generating SPY returns and Apple returns, kindly chat, please. So I hope you'll respond faster, class, so that we can save on time and cover more materials. When you're done, class, when you have loaded or created SPY returns and Apple returns, please chat so that I know. Thank you, Moises. Let's wait for the others. Okay, good. Thank you. All right. So what we now do is we create an object called combined returns. Again, class, you'll have to run this. Sorry for not giving this to you because I want you to practice. So we're going to merge, class, Apple returns, which is this is an XS object containing the returns of Apple, and then SPY returns, class. And then you recall what this all is equal to all equal false mean. Okay, it means that only put together those dates that are common to both. If there are dates that are missing in Apple or missing in SPY returns, please do not include. And just note, class, that this is the last thing that you should do, class. This is not a good way technically, class. Only for this subject. Just because I know that there are no missing values, I just wanted to introduce that concept. Because removing rows should be the last thing in your mind. The process of imputation exists. Okay? So when you have data that are missing, the last thing that you should do is to remove that data. Okay? Take a look first at what processes you can adapt in order to impute data on that. So before I told you about LOCF, last observation carried forward. Okay? So, and there are others, many others. So yung removing of the missing values should be the last thing in your mind. Just like this, all is equal to false. All right, then since the column names are Apple that adjusted, we replaced it by Apple returns and SPY returns. And then check if there are missing values. Because of this, all is equal to false. There should be no missing value. But then again, yung Apple and SPY are obtained from quant mode, same date, from at saka to. And I suspect that there should be no missing values there. Also here, check and a.omit if there are missing values. I'll give you a few seconds, please, and then please, once again, I would appreciate you confirming with your chat that you have already done this, okay, and you have the combined returns data. Thank you. Good. Thank you, Marcellus. Aiden, thank you. Okay, Paula, thank you. Thank you, Jello. Okay, Justin. So happy that you're responding quickly. Thank you, class. I really appreciate that. Kian, Justin, thank you. So a few more seconds, class. Kylie, thank you. Okay, while we're waiting for the others class, I think I failed to announce to you last time that uh, on Tuesday, I'm still not sure, class. I'm still not 100% okay. But if I feel if by tomorrow or by Wednesday, there's a marked improvement in my fit condition, then I'll see you on Tuesday. Otherwise, class, I hope please bear with me. I would rather that I ensure that my feet is, let's say, nearly completely healed before I go to school. Otherwise, because if I risk it, tapos baka it might worsen my condition, and that will prolong more the uh, the the difficulty I have. So I'll inform you ahead, please, and I hope you understand, class. I hope you don't take it against me. I really want to meet you already because we also have to meet. We also have to have a face-to-face exams already. Okay. So again, thank you for understanding. Okay, thank you so much for your cooperation. Okay. So we have this. I already gave this code to you. Yes. So for those of you, uh, I don't think any one of you were my student in FinStat before, because in FinStat we have this data visualization, almost 4 weeks of data visualization using ggplot, and we covered so many plots, different types of heat maps, etc., using ggplot2. And this is one example where you use ggplot2. So you notice that ggplot2 is all about layering. Okay, so you first define what your data is. Our data is combined returns. However, ggplot2 will not work if your data is XTS object. So here we're converting it first into a data frame. This does not mean that your combined returns will become already a data, which is an XTS object will already become a data frame. Okay, it's only in this particular code. And then after that, we mapping what's the x-axis and what the y-axis is. So you close that, open here, and then close here. Okay, and then plus. Okay, these are now the what type of plot or chart you want to put here. So this is geom point. It means scatter plot. Alpha is used for jittering. This means just to jiggle the data a bit. Okay, 0.5, and then color is dark blue, and then plus. You notice that the pluses class are at the end. You don't put it at the beginning because it will generate an error. And then GG title, because it's supposed to be at the end of your layer. Okay, so GG title is another layer plus X label is another layer plus Y label is another layer, and then you have the theme, the default minimal. So when you run this, you'll have this, guys. So it's a scatter plot between SPY returns and Apple returns. Now take note that when you're plotting for CAPM, okay, the market should be always on the x-axis. Okay, remember that, class. And then your asset should be on your y-axis. So if you take a look at this, SPY is the market, Apple is the asset. So this is correct. You don't invert it, class. And you can see here that there seems to be a strong relationship, positive, strong relationship between Apple and a positive, strong relationship between Apple and daily returns. Okay. All right. So let's go to the next plot, which I gave you, and it will just include as a layer an chat. So let's first run this class. Okay, I don't think I gave this to you also. So we're creating this object regression data df. Okay, you may name it differently, class. Just make sure that when regression data df appears in my screen, then you name it accordingly. Then as that data frame combined returns. Notice, class, that we are now creating another object, regression underscore data underscore data frame. Okay, and it's a data frame. We preserve combined returns, which is an XS object. So we're creating this object called LM model, and it's LM, which means linear model. So maybe for most of you, this is the first time you're using LM because you were not my previous students in FinArts. LM stands for linear model, and it's a power horse as far as regression is concerned. So we define first, we identify the dependent variable and then the independent variable. Dependent variable Apple returns, independent variable SPY returns. If you remember the one Moises shared a while ago, we are predicting the asset based on the excess return of the market, okay? Market excess returns, RM minus risk-free rate. So the risk-free rate acts here as a constant. Okay, so what do we have? What do we have now here? Okay, and then of course you define the data. Okay, and please run this, class. I'll run this now. And then insert here, include here, please, summary. And include here summary, LM underscore model. Right? So when we run this, class, you can see here the regression output. Okay, I'll pause for a while and kindly please, chat in the chat box. In the chat box, please, if you're done with the summary of LM model. Good, thank you. Very good. Yes, great. Thank you for this, class. I really appreciate the quick responses, and we're able to cover more materials and save on time. Good. Thank you. All right, let me continue. Okay, so very quick understanding of the output. I'm sorry I failed to ask you, how many among you are seeing this output for the first time? Yes or no, please? First time. The first time, yes. If not the first time, no. At least in R, I meant R. Okay, good, thank you. Others, please, you're seeing this output in R for the first time. If, okay, si Paula kasi student ko sa FinArts. Thank you, Paula. Okay. Yeah, good. Some of you, yes, some of you know. I think more no. Jeremy, di ba kita estudyante sa FinArts?
Nag-ano na po ako, FinArts na po ako, pero
So,
ilang terms ago na po.
oh, pero nakakita ka ng ganitong ano, di ba?
Yes po.
Oh,
Ibig ko sabihin po na nakita
oh,
ko na
so,
po siya.
okay. So, ang answer mo, yes.
Yes po, sorry.
Sige, sige, thank you. Nagulat ako kasi alam kong student kita eh. Diba? Tapos naka-known. Sabi ko, student kita before in FinArts. Anyway, so thank you, class. No? So for those of you who are new in using R and new as my student, then this is a very powerful output, class. Okay, before we look at this one, class, let's first take a look at what happened to the object that we created. Okay, didn't we create this object first? We created this object LM model. So let's take a look at what LM model contains. We created an object and it will be here, class. LM model. And it's a list, class. If we view this, it's a list of 12. Okay, take a look at this many outputs you have in this regression model. So first of all, it says that it's a list of 12 objects. Okay, LM. Number one is coefficients. And you can see it's a double, it's quantitative. Two objects here. Okay, and if we click this, you have the intercept and you have the parameters pi returns. And this is what we expected in the regression output. You have your intercept and our independent variable is pi return. So this is the value. This is beta null, this is beta 1. And the residuals class here. Okay, how many observations do we have in our data? 1, 2, 5, 6. And there are 1, 2, 5, 6. There are 1, 2, 5, 6 observations or residuals. I'll not discuss residuals here, class. Okay. Please watch the first video again in order for us to save time, because I really spent some time showing the class how this was generated. Okay, so that we save on time and cover more materials. I know that you're responsible enough to watch the first video and learn from that, class. Okay, so let me go back here. Sorry. So other things, not only residuals, we also have here fitted values. Here, class. Fitted values. What are fitted values? These are your predicted values. Okay. And we said that the actual value, which is your let's say for the first observation, Apple returns first observation minus the predicted value, the first predicted value will be your first equal to your first residual. Okay, you have your actual value, you have your predicted value or fitted value, then you have your residual. Okay, actual minus predicted is equal to residual. So that's a very simple and straightforward relationship. Okay, then we have others here. Okay, all right, so terms and model. All right, so let's now go here, class. And by the way, sorry, before I go, you can actually access this. Okay, let me just show you. So suppose, class, I want to access coefficients. Where can I access it? From the object LM model, LM underscore model. Okay, right? $. And here you have, class, the items that you can access. Let me just access coefficients there. Control Enter, and it will give us the intercept and the pi returns. You can access all the residuals, class. You can access all the fitted values because it's here, class. Okay, everything that's available here, you can access from the LM object. Okay. All right. And here, class, if you get the summary of LM model, it will give us the okay, summary model, class. So first, the call. It tells us what function did we use, LM, and what was the formula. And then here you have residuals. Now, take note that residuals are very important because you will have to test whether your model is the best linear unbiased estimator, the blue class, which I discussed in the first video. Best linear unbiased estimator. We'll be able to test that by doing residual diagnostics, by checking the residuals. Okay, and then what do you have here? Coefficients, class. This is your intercept, this is your pi returns, and then your standard error, your t value, and then your p value. So this one I just like to repeat. You can see here the number te to the negative 16. It simply means, class, that okay, it simply means that the p value, okay, it's now take note, it's not actually 2e to the negative 16. It's actually, it could be much lower than that. Okay, but I'm not sure if I discussed this with you before, but never mind. I'll just discuss it in the next few lessons. This one. Okay, but what this means is that you type 2, you write 2, and then from this one, go to the left 16 times. It's negative 16. Negative 16. Okay, and then negative 16 is here, and then put here your zeros. There will be 15 zeros. Okay, 15 zeros. So that's what this symbol means, this number means. And it's 3 stars. What do those 3 stars mean? Here it does. It's significant at 0.001. There. Significant at 0.001. If it was only that, then it's significant at just 10%. If it's 1 star, it's significant at 0.05, which is the threshold, because what we oftentimes use is that your level is of significance. This is now basic stat class, is 0.05. Okay, so let me just tell you that this one class, okay, involves an inferential test. This is not a descriptive stat. This is an inferential statistics, and it calls for a null hypothesis. The null hypothesis is that your beta 1 is equal to 0. So we're claiming here that your SPY returns does not actually have any relationship or association with your Apple returns. So is that true or not? You can find it here, class, in the probability, in the p-value. So the rule is when the p-value is low, class, when the p-value is low, the null must go. I use this because it's easy to remember. When the p is low, the null must go. They rhyme. It's easy to remember. What does that mean, class? Here, the p is really very, very slow. It's lower than 0.05. So that's what I meant by low. Low in reference to your alpha, your standard deviation. So our benchmark is 0.05. So low with reference to 0.05. And yes, it's really much lower than 0.05. So what's our inference? What's our conclusion? When the p is low, the null must go. So which means that let go of the null. We reject this. There's a strong statistical, we reject the null hypothesis that beta 1, okay, which is the slope, which is the marginal effect of SPY returns on Apple, okay, is equal to 0. It's not equal to 0. Statistically, it's a value other than 0. And the average, in fact, is 1.19. Okay, so what does this mean, class? For every 1 unit increase in SPY returns, there's a corresponding 1.18 units increase in Apple returns. Okay, which means that, okay, let's plot it here first. Okay, so I hope this is clear, class. Now your intercept, class, is not significant. Okay, no stars, not even a dot here. But the intercept is always included, class, in your model, regardless if your p-value is correct or not. So if we model now, if we create our model, we'll have Apple ret, class, because that's what we're modeling, is equal to your intercept, that's your beta null, that's your 0.003552, plus B1, which is 1.19, times your SPY returns. SPY ret, and then plus your residuals, epsilon sub I. Okay, so Apple ret sub I is equal to beta null. This is your beta null. You can replace it by 0.003552 plus 1.19 times SPY returns. So that's your regression model. So it's quite similar to your CAPM. However, we will have to change this a bit because here we did not use the return on the market class. And we did not choose, well, actually we use the return on the market because the return on the market is your SPY rate. However, we did not get the excess returns, the risk-free rate, the RFR class. So in our next activity class, we will do that. We will now simulate. We will now do CAPM class, strictly CAPM. This is not actually CAPM. This is just a simple linear regression relating SPY rate and your Apple rate. All right. And this one class, this is called your goodness of fit test. Your goodness of fit test uses the F test, F stat. Okay, and then you have 1 degree of freedom, DF1 and DF2. Okay. This is F stat, this is T stat. This is the individual fit test. This is the overall goodness of fit test or the joint test. I'm sorry. This one uses T stat, this one uses F stat. Okay, so I will not and notice class that the p-value is the same. Why is it the same? The goodness of fit test also has its hypothesis, and the hypothesis is that beta 1 is equal to beta 2 is equal to beta 3 is equal to how much is equal to beta sub n. How many predictors you have is equal to 0. So if you're doing multiple linear regression, this is your null hypothesis. But since we're only doing simple linear regression, since we have one predictor, then this drops out. We don't have other betas. So it's simply beta 1 is equal to 0. So it's similar here to our test here in the T-stat. The only difference is that this uses T-stat, this one uses F-stat. Okay? All right, so last one here. Also, I forgot to. Okay, this one class. Multiple R squared. What we're interested in is adjusted R squared, around 63%. So what does that mean? It means that 63% of the variation of your dependent variable Apple rate can be explained by your model. What's our model? SPY returns. Because in this case, we only have a simple linear regression. We were using SPY returns in order to predict Apple returns. So 63%. Okay. What does that mean? The 37% could be explained by other variables. All right. Okay. Ano pa? Okay. So close this. Okay. Quick pause class. Are you able to follow? Is my explanation very fast? Is it unclear? Do you want me to? I'm not presenting in Zoom. Class? Can you see my screen? Nina, you're not presenting here, so Zoom. Can you see my screen, class?
Yes po, sir. Kita po.
Okay, all right. So I got a message from one of you na hindi na present sa Zoom. I got nagpanic naman ako doon kasi sayang yung re-record natin. Okay, so I hope clear tayo, class, no? Okay, thank you. All right, so let's go now. So we discussed this, class. Okay, this plot I gave you, class, and notice what's different here is that I added this, class, geom smooth. We have this kanina. A while ago we had geom point. That's a layer, and then geom smooth. And method is equal to LM, color is equal to red, standard error is equal to false. What will this look like, class? Okay, what will this look like? It will now include the regression class using LM. Okay, and then GG title, XLab theme. Let's run this class. And when you run this, of course, I won't run it anymore. It's this one. So this is your regression model class. This one. That's your regression model. Okay, so you can see that, by the way, the standard error class, if you made it through, okay, you'll see a band here. It's not clearly seen because the standard error is very small. No? Okay, in fact, the adjusted R squared is quite relatively high, 67%. So the standard error will be quite small. No? So you can't, if you can see the gray area, okay, that's the band of your standard error. If you have a model where you have the residuals, the error terms are quite big, then you'll see this. You'll see that standard error quite big. Okay, so let me just put it back to false. All right, so let me move on, class. This one, class, is just a discussion of what we have done. Okay, I'll not belabor the point. I just place it in writing. Okay, so that you have a reference if you want to review your data. Okay. Now for this one, class, the coefficients, class, are they're what we call point estimates. But actually, okay, you can, when we do regression, your estimates have what we call an upper level and a lower level. In Excel, it's usually when you do regression in Excel, it's actually shown. But in R, you can get it, class. How can you get it, class? Okay, let's get LM model coefficients. We got this a while ago, right? And then we can use the function confidence interval for our regression model LM. So if you click this, class, if you run this, then you'll generate these results. And well, that simply means that for example, for your intercept, class, this is your 95%. Okay, this is your 2.5%. This one, class, 2.5%, 95%. So the total here is your 97.5% here. So if you get the confidence interval level, okay, for example, SPY returns, it's 1.19, okay, but it's between 1.14 and 1.24. And for as long as that doesn't touch your zero value, then that means that the probability for it to becoming zero is quite remote. Okay, less than 0.05%. Okay, take a look at your intercept. I'm sure you discussed this in your basic stat before. So you notice that the lower level is negative. The higher level is 0.001. So between these two values, you touch zero. So that's why your intercept is not significant, because it simply means that there's a probability that your intercept could be zero. For SPY returns, there is no probability that it will be zero. Okay, the probability is very, very low. Okay, that's why we're rejecting, going back again to the null hypothesis, that your beta 1 is equal to zero. Okay, we reject this because based on your confidence interval levels, okay, you will never get to zero here between 1.13 and 1.24. Okay, so that's just a quick review of your basic stat. but in R, okay? So in R, it's very easy to get those values. Okay, so this is the confidence in the goodness of fit that I was mentioning to you about. You have your multiple, you have your R squared and your adjusted R squared. Okay, now let's quickly, okay, still have time. Let's quickly take a look at, let me share this with you because I don't think I shared this with you. Okay, Control C, Control V, just copy that please in the interest of time. Okay, I know you can do this, but because we don't have much time. Okay, take a look at this class. Sum of the squares total, sum of the squares regression, or so regression sum of the squares, and error or residual sum of the squares. Again, this is just a quick review because you have discussed this. Let's just use R for that. Total sum of the squares. It's your actual value minus your mean value. Okay, what does this mean? What does this imply? This implies that, okay, I will not use pi returns. I'll just use the value of my data, of my independent variable. Okay, Apple returns, just get the mean. Whatever my actual value is, my predicted value is my mean. Okay, so that's what this means, class. Your predicted value minus, your actual value minus what's your predicted value here? Your mean. Okay, so you're not using any, okay, you're not using any exogenous variable. You're not using, in this case, Spiret. You're just using Apple itself. So this is called your total sum of the squares. And now here, class, you have your regression sum of the squares. It's called our improvement because initially you were using just the mean, but now you're using the predicted value, which means that you're using an exogenous variable. The exogenous variable is your SPY returns class. Okay, so the difference between your SPY returns minus your mean value, because initially you just use your mean value. Okay, so this is now an improvement in your model. So we call it regression sum of the squares. And lastly, your residual sum of the squares, which is, we have been discussing this, the actual value minus the predicted value. What your prediction, the difference between your actual and your prediction, okay, will be your residuals. So the relationship between this is SST, total sum of squares, is equal to SSR plus SSE. Okay, I think this is what I gave you. Okay, so let's just quickly class. Dito lang natin, let's together na lang class, together, Control Alt I. Let's compute SST, SSR and SSE. The good thing is that this is easily computed class. All right, so SST, capital SST, is equal to, okay? So first let's get y sub I. Where can we get y sub I, class? Anyone please tell me, where can I get y sub I? Y sub I are your actual returns. Where can I get the class? Hello? Anyone please? Quick answer please. Where can I get my y sub I? Okay, so let me just answer that, class. Your y sub I, class, can be obtained from your actual data, right? You have your, where is that, class? Your regression, your combined class. Where's our regression? Here, class. Here. Regression data DF, right? This is your, or you can use your combined returns, or your combined returns is X as object. That one, regression DF, is your data frame. So let me use that, class. So Control V, that one, class. How do I get my y sub I? Dollar. Iba Apple returns. So this is our y sub I, all your actual Apple returns. And then we subtract the mean. Ba? So minus mean. mean, same. Mean of your Apple returns. Okay? And then what we have to do, class, is that we have to square this. So I'll put here parentheses, close parentheses, and then squared. So this takes care of this one, class. This one. Y sub I minus Y mean, and then squared. And then once we have squared it, class, okay, once we have squared it, we add. Okay, let's just run this first, class. And that's not actually your SST. So if I go here, where's our SST? Here, class, SST. Oh, wait, what happened? YNA. Something wrong here? Is there anything wrong? Mean default regression. Huh? Not numeric? What's not numeric? Sorry. Where's regression? Ito, di ba? Let me see. This is our object. What's not? I'll run this first, class. Oh, that's numeric. Those are the returns, right? And then I'll run this mean. Sorry. Not mean. I'm sorry, class. There's no such thing. It should be average. There. I'm sorry, class. Yeah, my mistake. Average. Oh, yeah, it's mean. Sorry, wrong again. Mean. Mean of regression, DF, okay. NA, why NA? Why NA? Is there an NA here in regression? A moment, please. Okay, let me check. Control Alt I. Sum is that NA regression. Okay. Wala. Wala naman NA. So why? Okay, let me see, class. Let's just first use, I'd like to see if here, Control Alt I. I'm sorry, class. I'm wondering why I'm getting wrong here. Control C, Control D. Let's use instead the,
Sir,
yes?
dun po ata sa mean ng
Mm-mm.
regression data
Yeah.
frame, hindi po na-extract yung AAPL na return.
Ay, sorry. Thank you. Oh, thank you. Sino that? Who's that? Yeah, my bad.
Moises po.
Moises, thank you. Siguro, I'm sorry, class, because of I was pressured to move. Yeah, you're correct. Very, very good, Moises. Thank you. Yeah, very, very wrong on my part. We have to use the, we're getting the Apple returns. Yeah, that's why, class. That's why. Okay. Sorry about that. My apologies. Very bad on my part. Okay. So regression data, this is now correct. Okay, so let me run this first. If I run this class, Control Enter. Okay, let me print SST. SST. Control Enter. There you go. So these are now the differences between your Apple returns and the mean. So you keep on subtracting your Apple returns to the mean, and there's only one mean, right, class? There's only one mean. Okay, if I run this regression here, Control Enter, there, it's 0.00532. Okay, so you have 12,156 observations of Apple returns, and then you keep on subtracting it to this mean. Okay, so once we have subtracted it, class, then we have to add. Okay, so be careful about this, class. So we have to put this, we have to sum, open parenthesis, sorry, sum, open parenthesis, oops, and close this. All of those differences, class, you add all of them here. Okay, so that's your SST, total sum of the squares. Okay, so let me just delete this because it's eating up so much space. Okay, so let's run this. So this is now your total sum of the squares. All right, and then, class, we compute for SSR. So again, one at a time, SSR, capital, is equal to, take a look at the formula, step by step, your predicted minus your mean. Okay, we have the mean, class. This is your mean. Let's get the predicted. How do we get the predicted, class? Okay, LM underscore model, LM underscore model, dollar, class. We get the fitted values there. Okay, if you run this, class, Control Enter. Okay, those are your fitted values. Those are your predicted values. Where did they come from? They came from the model. Okay, they came from beta null plus beta 1 times x. Your x are your SPY returns. Okay, so you also have 1,256 predictions because you have 1,256 SPY returns. All right. So what do we do with this, class? We subtract the mean. Right? So those are your predicted values minus the mean. This is the mean, right? Okay, so as Moises correctly pointed out a while ago, I failed to get, where am I? Bakit SPY returns to? Mali ito, class. Na-press ko dito. Sorry, class. This should be, ay, nako. Mali, class. Sorry, ha? Apple returns to, class. Why mean to, class, eh? This is the mean of your y variable. Okay, so that's wrong. There, 0.499, 0.4 something. All right, then your SSR, okay, mali na naman to, no? So this should be dollar, Apple, tab, yan. Okay, so this is your fitted value. Class, it's already time. Just feel free to leave, class. I'll just end this for the tape, for the recording. Okay, so that's why this is your predicted minus your mean, and then, okay, and then we have to square. We have to put this in parentheses, and then parentheses, and then square it. Okay, this is already squared, and then sum. So put everything in parentheses. Okay, parentheses here, and then put the sum function there. Okay, there you go, class. What's wrong? 1, 2. Ano naman mali ko? What's my mistake here? 1, 2. 1, 2. Did I miss out something here, class? Tama naman. Regression data. Oh, it's wrong. Squared. Wrong daw, sabi ni R. Unexpected token. But we're still going to sum it, di ba? Mali ito eh. O bakit? Nawala na yung sum. Mali ito. Why this one? Ah, sorry. Wait. Lit class, huh? Sorry. So, let me remove first this one. LM minus min, okay. Then we square. We have to put it in parentheses. This one. Square that. And then sum the whole. Parentheses here. Sum, parentheses here. Now it's okay. A while ago, why did it register? R is fooling me. Okay, there you go, class. Sum of the squares of regression. Okay, which means, class, of the total variance, 0.499, 31.31 is explained by regression. So we can get here, class, yung R squared. R squared, I'll end in this one, R squared is equal to your SSR divided by SST. Control Enter. So everything. Where's R squared? Just make it RSQ. Okay, print. Their class. 62.81. Asan yun? Here, class. So it's your multiple R squared. Okay. All right, let me stop here. And thank you for your patience. Thank you for those who are still here. Okay.